Hello Year 11, it's Mr. Green here. I'm going to take you through the first lesson of the second topic in Year 11, which is waves. First lesson we'll be looking at the properties of waves, and the learning objective is to describe longitudinal and transverse waves. If you could pause the video while you write that down as your title today. Okay, so retrieval practice to start with, 5 questions based on our previous learning. Again, if you could pause the video while you attempt these 5 questions, give yourselves 5 minutes to do that, and then restart and we'll go through the answers. Okay, so question 1, units of force, they would be newtons. Question 2, what is stopping distance? Stopping distance is thinking distance plus the braking distance. Question 3, what would thinking distance be affected by? Well, thinking distance is about the driver. It's about how the driver reacts. So that would be affected by being tired, by alcohol and drugs, or by distractions in the area. Question 4, what is braking distance affected by? Braking distance is more about the car. So that would be affected by the condition of the road, the condition of the tyres, and the condition of the brakes. Any of those things are worn, then the car's going to travel further when you apply the brakes. Question 5, what's the unit of energy? Energy is measured in joules. Okay, learning outcomes for today's lesson. We need to know that waves can be longitudinal or transverse, know the difference between longitudinal and transverse waves, and know what waves transfer and what is not transferred. So we start with a brief picture. What's happening in these two pictures? At the top, we've got air molecules that are associated with sound, and we've got large bunched together areas of that and areas where they're spread out, and we're showing the propagation of the sound going to the right. Beneath that, we've got a water where something's been dropped in there. But what we get here is we're getting two different versions of waves. We've said there are two types of wave, transverse and longitudinal, and this is a brief introduction to what those waves look like. So a wave is an oscillation or a vibration that transfers energy but doesn't transfer matter. So the object itself vibrates and energy emanates from there, but matter or mass itself doesn't go anywhere. There's two types, either longitudinal or transverse. Sound waves are longitudinal, and light and other electromagnetic waves are transverse. You may be asked for examples during the examination. There's your two banker examples. Sound waves are longitudinal, light and other EM waves are transverse. Pause the video and copy those definitions down, please. Okay, so we start off with our first wave, a transverse wave. A transverse wave looks like the wave we've got on the front there. It's where the particles would move up and down. So the particles would vibrate up and down, but the wave itself would move to the right in this case. Definition there is the oscillations are perpendicular, which means at 90 degrees, to the direction of energy transfer of the wave. So what type of wave is ripples on water? It's this type of wave. It is a transverse wave. If we can see there, if you focus on one of those particles, you can see that it doesn't move from side to side, it only moves up and down. But the wave itself is moving from side to side, it's moving towards the right. Particles themselves move up and down. So again, it makes this explanation proper. The vibrations are up and down, energy transferred in that direction. The vibrations of a transverse wave are perpendicular to the direction the wave transfers energy. Pause the video, copy that definition down. Next one. We can make waves on a rope by moving it up and down, and that would be a transverse wave. Again, showing us that definition. They are perpendicular to the direction energy is transferred in. A Mexican wave at any sort of sporting event, that would be a transverse wave. The people are moving up and down, but we see the wave moving around the stadium. Different type of wave than longitudinal. Now in longitudinal waves, the oscillations are parallel to the direction of energy transfer of the wave. That means they travel in the same direction. We have a spring there, and we can see when we set a longitudinal wave up, part of the spring squeezes together and part of the spring is far apart. You'll see that compression travels further and down there. We'll see some videos in a second where that takes place. The oscillations, so the particles themselves are moving left to right, and the wave is moving left to right as well. Now we need to know these expressions, compression and rarefaction. Compression is where it's squashed together, rarefaction is where it is spread out. There's a longitudinal wave. Now focus on again one particle and state what it does. If you look at one particle there, it will only be moving from side to side, vibrating from side to side. No particle travels all the way along that. They're all just vibrating side to side. But if you take a step back and have a look at it, you'll see that there is a definite compressions and rarefactions. Compressions are where you can see the wave, rarefactions are inside there, so they're the ones in the middle where there's very few particles. So the vibrations are in the same direction as the energy transfer. So here's our definition. Longitudinal waves. The vibrations of a longitudinal wave are parallel to the direction the wave transfers energy. Pause the video, take that down. Okay, so we can make waves along a slinky spring by pushing and pulling one end. And again, it gives us the same definition, parallel to the direction the wave transfers energy. We can see the differences between the two waves there. Wave A is transverse and wave B is longitudinal. Again, transverse, the particles would move up and down, but the wave itself moves from side to side. In longitudinal, the particles move from side to side, the wave moves in the same direction. Again, there's a longitudinal wave. We can see the compression and the rarefaction. We can see it moving along that slinky, moving along that spring. So ensure you've got these down, the displacement and the direction of the wave. That's how we define transverse and longitudinal. Transverse waves are where the vibrations are at right angles. Longitudinal are where the vibrations are parallel to the direction of the wave. If you haven't got those down yet, pause the video and make sure you have them. Okay, so do particles get transferred during transfer of energy? So every single wave transfers energy in the direction in which they travel, but no wave transfers matter. Whenever a wave travels through a medium, whether that's air, water, a solid, the particles vibrate and transfer energy between each other, but overall the particles stay in the same place. Only energy is transferred. Again, pause the video, copy those down. That's information you may need to give back in an examination. Okay, a few questions for you here then. So question 1, 2, 3 and 4. I'm going to ask you to pause the video and attempt all 4 questions. Once you've attempted them, I'll put the answers up for you so you can see how you've done. Okay? Okay, question 1. Waves can be transverse or longitudinal. What's meant by a transverse wave? Transverse wave is a wave at which the oscillations are perpendicular to the direction in which the wave travels or transfers energy. Question B. Give an example of a transverse wave. Any electromagnetic wave, ripples on water, waves on a string, a slinky wiggled up and down. Again, if you need to, pause the video at any point to make sure you've got these answers correct, or to get a green pen to show that you're changing and you know what you're doing. C. What's meant by a longitudinal wave? Longitudinal wave is a wave in which the oscillations are parallel to the direction in which the wave travels or transfers energy. Question 2. What's meant by the areas of compression and rarefaction in a longitudinal wave? In areas of compression, the particles are bunched up close together, and in areas of rarefaction, the particles are more spread out. Again, if you need to change your answer or get this down, please pause the video and do so. Question 3. Which of the following waves is longitudinal? Light, sound, or water ripples? Light's an electromagnetic wave, so that would be a transverse wave. Water ripples, we again look at our model, the particles move up and down, but the wave itself moves from side to side. That would be transverse, so the only one would be B. And finally, do water waves cause water molecules to travel across the water's surface? The answer to that would be no. Describe an observation that supports this. Any object placed on water, like at the sea, will bob up and down on the ripples and will not move across the water. Okay, that's it for the first part of this lesson. Again, make sure you've got all the information down. Rewind and see if you've missed any sort of information that you feel will be important, or just to review it again. Next lesson will be coming up and is about the structure of the wave. Okay, thanks very much for listening. Goodbye.